Okay, now that we know how reactions happen, we can start to think about how each factor affects the rate of a reaction. So, to make this perfectly clear as we're going through, what we need to do is we need to relate these two requirements for a reaction to happen. So they have to collide with each other and they have to have the enough energy in order for there to be a reaction. How can we relate that to affecting the rate? So the rate, okay, the rate will change if we, number one, change how frequently the particles collide. Or two, change the proportion with the activation energy. So, when we're thinking about each of these four different factors, temperature, concentration, particle size, and presence of a catalyst, we're going to think, does it change how frequently the particles collide? Does it change the proportion of collisions with the activation energy? And if it does change one of those, it will affect the rate of a reaction. Okay, because if it increases how frequently the particles collide, that will increase the rate, and if it increases the proportion of collisions with the activation energy, that will increase the rate. Okay, so let's start. Number one, temperature. Okay, so as temperature increases, what happens? Well, the first thing that happens is the particles get more energy. All right, so the particles have more energy. That's what it means for temperature to increase. It means that particles have more energy. So if you increase the energy of each particle, that's the same as increasing the temperature. And when you increase the temperature, all the particles have more energy. All right. So what does that mean? Well, if the particles have more energy, then they will move faster. Okay. And if they move faster, it stands to reason that what's going to happen? Therefore, they will collide more often. Okay, so now we can see that if we think about it, have we changed how frequently the particles collide? Yes. By increasing the temperature, we give the particles more energy, which means they move faster, which means they collide more often. All right, so that's going to increase the rate. All right, but let's not get ahead of ourselves. Let's think, what else will happen? All right, well, if the particles have more energy, will that change the proportion of collisions with the activation energy? Yes, it will, because we're giving them more energy, therefore more of them will have enough energy for the collision to be successful. Remember over here we said the colliding particles have enough energy to react. If I give them more energy, more of them will have enough energy to react. Okay, so we can say here that a larger proportion of the colliding particles have the activation energy. Okay, and that then is also going to increase the rate. Okay, so we've hit on the first one, on temperature, we've actually managed to change both of these. All right. So we're not finished yet, okay, because we haven't linked this to the rate. Okay, so this is how we do it. All right, this is very, very important. So as temperature increases, particles have more energy. They will move faster and collide more often. Also, a larger proportion of the colliding particles have the activation energy. All right? Therefore, the frequency of successful collisions will increase. And the rate will increase. All right, and it is crucial that you say that line here. So this is really important. I want you to now do two things. Whenever you talk about this kind of situation, you need to refer to how it affects the frequency of successful collisions. That phrase. How does it affect the frequency of successful collisions? And the second thing you need to do is you need to always, 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 at the end, relate it back to the rate. So if I were to ask you the question, how does increasing temperature affect the rate? You need to say, well, blah, 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 blah. Therefore, the frequency of successful collisions will increase and the rate will increase. Okay, now, the reason that I've chosen to do this topic remotely ahead of time is because it comes in these nice little sections like this, okay, that are very self-contained, that you can easily put on a flashcard. So, you can make yourself a flashcard now. Effect of increasing temperature and rate of reaction. And then on the flip side, we will have, number one, particles have more energy, move faster, collide more often. Number two, larger proportion of colliding particles have the activation energy. Number three, therefore, frequency of successful collisions increases. And number four, because I've asked you, on the reverse side here, I say effect of increasing temperature on rate. What is that effect? Rate increases. Okay, and that is a really good flashcard for you to have, because if you can remember all of those things there, you know exactly what is happening when you change the temperature in a reaction. Okay, now obviously this works for the opposite case. If you decrease the temperature, then it's just all the opposite things. Okay, so they have less energy, they move slower, collide less often, a smaller proportion of the particles have the activation energy, therefore the frequency of successful collisions will decrease and the rate will slow down. All right, good. Okay, number two. All right, so let's move on to number two. Concentration or pressure. Okay, so concentration and pressure are more or less the same thing, because concentration is just the number of particles you have in a liquid usually, and the pressure will just be, you know, it's the same thing for a gas. If I increase the concentration of a liquid, I put more particles in. If I increase the pressure of a gas, I put more particles in, or I make the volume smaller. Okay, so they are more or less the same thing. So, as concentration or pressure increases, all right, what happens? So we have more particles in the same volume. more particles in the same volume. All right. So what? Well, if you have more particles in the same volume, then the particles are closer together. So we haven't changed the speed, we've just put them all closer together. Now if they're closer together, what will happen? Well, they will collide more often. Therefore, they will collide more often. Okay? Now, so what we've got is our two requirements to change the rate of reaction. We've changed the frequency of the particles colliding because they're closer together, so they collide more often. Now, are we going to change the proportion of collisions with the activation energy by doing this? Well, no, because I haven't done anything to the energy. I've made no changes to energy. All right? All I'm doing is I'm making the particles closer together, which means they collide more often. So there is nothing to do with energy here. Okay, so we don't need to worry about that. This is simpler than temperature. But we have changed one of those requirements, so we do have an effect on the frequency of successful collisions, because if you increase the number of collisions, you will, of course, increase the number of successful collisions. Therefore, the frequency of successful collisions increases and the rate increases. All right, nice and simple. Okay, and you can put that on a flashcard. In effect of increasing concentration or pressure on the rate of reaction. Okay, you can say on here, more particles in same volume, particles closer together, and then you can just skip right ahead and just say increases frequency of successful collisions, increases rate. Okay, and then there again you have this nice contained situation for concentration and pressure. Okay, and you're going to have one for each one. So temperature, concentration, pressure, and then particle size and the presence of a catalyst. Okay, now that we've done temperature and concentration, I want to think about how we can see the effect of these in the graphs that we would draw. So remember from last week, we drew this graph here. Okay, and we thought about how that told us about the rate of reaction. We're going to do the same thing. All right. So imagine that this graph here is the reaction. Let's do the same we did last week. So it's magnesium plus hydrochloric acid gives me magnesium chloride plus hydrogen gas. Okay, so that's a gas, and we're measuring the volume of that gas coming off in our reaction. All right, and let's say that this reaction here is 1 gram magnesium, and it is 1 mole per decimeter cubed HCl in excess. Okay, and this is just a measure of concentration. We've missed out the concentration chapter. All right, but we will do that, so you'll understand that. At the moment, you just need to know that it's just 1 and then the units of concentration. Okay, and it's excess, which means I've got more than enough hydrochloric acid. All right, so my hydrochloric acid is not going to run out. My magnesium will run out. All right, so what's happening? Well, the reaction happens. Okay, so the volume of gas increases, and then it starts to slow down, and then the reaction stops. Okay, so that's what happens here. So here, where it goes level, we can say the reaction has finished, because no more gas is being produced, which means that no more H2 is being produced, which means this reaction up here is not happening anymore. All right. Now let's suppose that we do this reaction with our acid is at 25 degrees C. All right, room temperature, slightly warmer than room temperature. Okay, now I'm going to do the same reaction, again, but this time I'm going to do it with 1 gram of magnesium, 1 mole per decimeter cubed HCl, again in excess. But this time I'm going to heat my acid up first, and I'm going to do it at 50 degrees C. Have a go now and draw what you think the graph would look like for that reaction. Okay, well, hopefully you've thought, well, 25, 50, that's the only thing that changes, so I've gone higher temperature, which means that the rate of reaction is going to increase, so it's going to have a steeper gradient. So hopefully you've drawn something like this. Okay, now the reaction finishes at the same volume, so the volume of H2 produced doesn't change, but you just get there quicker. All right, so you can say here the reaction finishes quicker. Okay, and it's really important that you realise, by looking at these two graphs, increasing the temperature doesn't give you any more gas. It gives you the same amount of gas quicker. All right, so you increase the rate, you don't get anything more, you just get the same stuff but sooner. Okay? So let's have a go at another one. Let's go down here and we'll do 1 gram of magnesium again. This time we'll do 0.1 mole per decimeter cubed HCl, but it's still in excess, so there's still enough of it, but I'm just using a lower concentration. So up here I was using 1 mole per decimeter cubed, now I'm using 0.1 mole per decimeter cubed, so it's a lower concentration, and we're going to do it again at 25 degrees C. What do you think the graph for that would look like? Okay, so hopefully you've thought, well, if the acid is still in excess and I'm using the same mass of magnesium, it means that I'm going to finish up with the same amount of gas. So I'm still going to end up at the same point. It's just whether or not I'm going to get there faster or slower. Now, here I had 1 mole, here I have 0.1. So the concentration is decreased. And if the concentration decreases, the rate decreases. And if the rate decreases, the graph will look like this. Okay, obviously it doesn't have to look exactly like my graph, as long as it has a more shallow gradient than this one, then you're fine. All right, so you see it takes longer for the reaction to finish. So the reaction finishes slower. All right, so you can see there that, you know, by changing the concentration, changing the temperature, we're going to change all of these things. All right, but I've got one more here. Okay, so I'm going to give you a slightly more challenging one. All right, so let's do, I'll write this down here. Might be a clue to what the graph looks like. 2 grams of magnesium, 1 mole per decimeter cubed HCl excess, and we're going to do it at, we'll do it the same as we did this one up here. So this one up here we did at 50, we'll do this one at 50 as well. So what would the graph for that look like? Okay, so what you should have noticed is that, well, if I'm still got an excess of acid, but I've doubled the amount of magnesium I use. Now, if I look at my equation, if I use twice as much magnesium, I'm going to produce twice as much hydrogen. So this graph, well, up here I had 1, 2, 3 lines of hydrogen gas. So down here I'm going to have 1, 2, 3, 4, 5, 6 lines of hydrogen gas. So it's going to end up here. But other than that, the concentration is the same, the temperature is the same, as up here. So I would expect the rate to be the same until I get up to here. So you should have something that looks like this. Okay, good. All right, so the reason it's twice as high is because I've used twice as much of the reactant, but this slope here and this slope here are the same because I'm still using 1 mole per decimeter cubed concentration and 50 degrees C. All right, excellent. So that is quite a long one, doing temperature and concentration. All right, so in the next video, I'm going to do particle size and the presence of a catalyst. Those are slightly quicker. All right, so you might want to take a break now and then come back in a few minutes for the last video.